All right. A lot of colds today. Okay, so yesterday we were going over substitution and indefinite integrals. We're going to keep going over that, and then we're going to go over these substitution and definite integrals. So this time we're going to use trig identities to set up a substitution. Okay. So we're going to go over trig identities here. Okay. So for this first one, I gave you the hint to rewrite it in terms of sine and cosine. And we need to see how that helps us here. Okay? Yes? No. Okay. So for this, if we're going to rewrite it in terms of sine and cosine, how do we rewrite this one? We're going to the integral of cosine of 7x over the sine of 7x. Good. Okay? They can't hear anything you're saying. You're too far away. No, so stop talking. Okay? So if we got a cosine of 7x over sine of 7x, we need to think about which one do we have a derivative on, what do we need to introduce here, and which one does it make sense? Would it make more sense to have du dx on the top or on the bottom? The top would be a lot easier, right? If we divide by du dx, that's going to be a problem because then it won't cancel out, right? That'd be like multiplying by dx du. So we want the derivative to be on the top. So the bottom is going to be our main function. So our u is the bottom, the sine of 7x. So just like cosine of sine. Oh, cotangent is cosine of sine. Yeah, you should know that. Yeah, that's one you should know. And then du dx, so the derivative of sine of 7x would be what kind of rule? Chain rule. Okay, so what would the derivative be? 7 cosine of 7x. Okay, so what am I missing in this integram here? I've got the cosine of 7x, I'm missing the 7. So I have to introduce that part into my equation. So if I introduce a 7, I also have to multiply by 1 over 7. So I'm going to put the 1 over 7 on the outside, and the 7 is going to go on the inside there. Oh, sorry, that'd be cosine of 7x. Over the sine of 7x. Okay? That's dx. Okay, so if I've got this, can I rewrite it in terms of u and du dx here? So what would it be? It would be 1/7 integral u dx over u and then dx, right? An easier way to write it would be to bring the du dx off to the side. So I'd have 1/7 smart boards on its lines. So what happens with the dx's then? They cancel and I'm left with 1 over u du. Right? That was one of the ones that we had talked about. It was going to be pretty important here. So we've got 1 over u du. We go back to the rules. I even got it highlighted. Then u to the negative 1 over on this side here. It's going to be the natural log of the absolute value of u. Okay? So we have to plug in. So it's going to be natural log of the absolute value. So we've got 1 over 7 ln of u, absolute value of u, plus c. Okay, and then what was u? U was equal to the sine of 7x. So my end answer is going to be 1/7 ln of the absolute value of 7, or no, sorry, not 7 sine x, sine of 7x, right? Yeah. Sine of 7x plus c. Okay? The du? Well, no, I mean, there's still a constant c. But the du dx is going to cancel out with the dx. Is that what you're asking? Yeah, so yeah, the du dx should always cancel. If we're doing it right, it should cancel out with the dx. Okay, if it was like du dr, it should cancel out with the dr. Okay, so whatever it is. Okay? So you guys try and set this next one up with a u and a du dx. I want you guys to think about how to set this up. We don't want the 2x to be the u. So we need to think, we're doing trig identities. So what is a trig identity we can get out of this one? 1 over cosine is what? 1 over cosine isn't sine. 1 over cosine is secant. So what is 1 over cosine squared? Secant squared. So we need to rewrite this. So if I rewrote this as the integral of secant squared of 2x dx, could you guys figure out what's going to be a little easier here? What has a derivative of secant squared? And tangent. Yes. The derivative of tangent is secant squared. So what would the derivative of tangent of 2x be? Right, because you've already got a 2x to limit. So what am I missing on the outside of the integrator? 2. So I'm going to have to divide on the outside or multiply by 1/2 on the outside. Okay, so what's going to be u in this case? Do we want secant squared of u? Do we want u to be the secant squared?
Yeah, we want u to be secant squared of 2x.
We want u to equal secant squared of 2x. And du dx would be secant of 2x, tangent of 2x, and yeah.
Will we keep the secant squared for u dx?
Oh, it'd be 2 secant squared of 2x tangent of 2x. Do we have that in our problem? No. We don't have the 2 secant squared tangent. So I don't think that's what we want our u to be. So what did we find the derivative of was? Well, I want to see what we want to find the antiderivative of here. So, Ermal, what is our main function and what is the du dx? What was the purpose of bringing the 2 in? That's the derivative of what? 2x. So if I had u equal to 2x and du dx equal to 2, then I would have 1/2 integral of secant squared of u, then u dx dx, right? We find the antiderivative of this because the derivative of tangent is secant squared. So this is where we can, the u was only that little bit there. So we've got 1/2 tangent of u, right? Because those dx's cancel out. Okay? Change your color. That's du dx.
Okay.
Right? So we replace that with the du dx right there.
So, okay.
Du dx right there. Okay? And then we need to add c. Didn't work. All right, can't change it. All right. Okay, so what was u? U was what? U was 2x. So we'd have 1/2 tangent of 2x plus c. Okay, now if we were to take the derivative of this, what would we get? Say we took the derivative. Let's double check on work. What's the derivative of tangent? Secant squared. Secant squared of 2x times 2. And then we had the 1/2 out in front. The derivative of the constant is 0. The 1/2 and the 2 cancel out, and I'm left with the secant squared of 2x, which is what we started with in the beginning. Okay? We put the 1/2 and the 2 in there to cancel each other out. That's why we introduced them. Okay? So for that, now we're done with the substitution. You guys should be able to get that on the homework tonight. Okay? Now we're going to go over substitution in definite intervals. Okay? There's an extra step that we have to take here. Okay? So we need to come up with a function and its derivative inside our integrand here. So what do we see that has its integral inside that integrand? Or I'm sorry, its derivative inside that integrand. Mostly. No, we can leave it as tangent and secant squared. There's no problem with having it as tangent and secant squared here. Look at each one of them separately. I've got tangent, and then I've got secant squared. Okay? The derivative of secant squared, is that going to be tangent? No. But the derivative of tangent is that secant squared. So the tangent can be my base function, or my u here. So u is going to be the tangent of x. And the derivative of u, du dx, that's the secant squared of x. So that accounts for everything right there, right? Okay. Now the problem with this is the extra step that we have to do. Before we didn't have any limits. Okay, so if I'm going to rewrite this, I would have u dx dx, right? If I'm rewriting it, tangent of x is u, secant squared of x is the du dx, and then we keep the dx out there. Okay, the du dx is going to cancel out with the dx, and I'm left with the integral of u du. But the problem here is, when I was dealing with tangent of x and secant squared of x, my limits were 0 to pi over 3. Okay, but when we deal with definite integrals, the limits are going to change. What do you think we're going to do to change the limits here? What? Not going to restrict the domain necessarily. Well, because that's not what we want to do here.
Would you like plug it into the one? Let's take that y value and set that y value into the new function.
That's what I would do. We're going to take the 0 and the pi over 3, and we're going to take u of 0 and u of pi over 3. And that's what's going to go in our limits. Okay? So we're going to look at the tangent of 0 and the tangent of pi over 3. Okay, so separately here, I need to look at the u of 0 and u of I would agree.